let's go over solutions to exam 2 review. So number 1 says take a few derivatives, take 7 derivatives. The first one, y equals secant of root 5x plus 1. Well, we have a secant function. The derivative of a secant function is secant tangent. So we have secant of root 5x plus 1, tangent of root 5x plus 1, but then we need to multiply by the derivative of root 5x plus 1. So we have 5x plus 1 to the half. The derivative of that is half 5x plus 1 to the negative half, so I'll just write that as, so I'll say times 1 over, so half 5x plus 1 to the negative half would be 1 over 2 root 5x plus 1. But then again, we have to multiply by the derivative of this inside. Derivative of 5x plus 1 is 5, so you could say 5 or times 5 out there. I'll just multiply by the 5 up there. So we have secant of root 5x plus 1 times tangent of root 5x plus 1 times 5 halves with a root 5x plus 1 in the denominator. Number 2. Well, not number 2, part B. The derivative of y equals the inverse sine of x to the 10th minus e to the x. Well, here we have an inverse sine function. The derivative of an inverse sine function is 1 over root 1 minus the inside squared. So let's extend that fraction bar a little more. So the derivative of inverse sine is 1 over root 1 minus the inside squared. But now we have to multiply by the derivative of the inside, and I'll do that by just putting it in the numerator. Derivative of the inside, 10x to the 9th minus e to the x. That was B. Maybe I should write B since I wrote an A and I'm writing a C. Part C. Y equals x to the negative 5th log of 3x. Well, here we have a product. So to find the derivative, we will apply the product rule. So dy dx is given by the product rule. So we have negative 5x to the negative 6th, leave log 3x alone, plus x to the negative 5th times the derivative of log of 3x, which is 1 over 3x times 3. And you could leave it like that. I'm going to simplify that second term just because having a 3 in the top and the bottom, I don't really like how that looks. So we have the 3 and the 3 cancel. X to the negative 5th, another x in the denominator becomes an x to the negative 6. So that second piece simplifies nicely. It's a cotangent of 2x. You don't have to factor out well, you actually didn't have to do that step of simplification, but you also don't have to factor out an x to the negative 6 since they exist in both terms, or it exists in both terms. So here, again, we have a product rule. Well, we have a product, so we will apply the product rule. The derivative of 3 to the x is 3 to the x log 3. Leave the cotangent thing alone. Plus 3 to the x times the derivative of cotangent of 2x. Derivative of cotangent of 2x is negative cosecant squared of 2x, but then times 2 because the derivative of 2x is 2. And I put the negative out there. part E. Oh, that looks like fun. Y equals x to the 7th minus 4e to the 3x plus 2 pi all over x e to the x minus 1. So here we have a quotient, so we will apply the quotient rule. So remember, quotient rule: bottom derivative top minus top derivative bottom over bottom squared. So we have bottom times the derivative of the top, 7x to the 6th, negative 4 carries through, derivative of e to the 3x is 3e to the 3x. So we get a negative 12 e to the 3x. Derivative of 2 pi is 0 because that's a constant. So we have bottom derivative top. Now we need to do negative top derivative bottom. So we have negative top is what? X to the 7th, negative 4 e to the 3x plus 2 pi. Derivative of the bottom, well, for x to e to the x, we have another product rule. So x e to the x, we use the product rule. Derivative of x is 1. Leave the other one alone. Plus x, derivative of e to the x, is itself. And then the derivative of negative 1 is 0. So by product rule, the derivative of x e to the x is 1 times e to the x plus x times e to the x. And then this is all over bottom squared. So we have bottom, derivative top, minus top, derivative bottom, over bottom squared. Now next we have a function that is not solved for y, and it doesn't look like it can be explicitly solved for y. So we will differentiate implicitly. So we have x squared y minus x y squared equals 3 minus log of x with base 5. Well, to differentiate implicitly, we take the derivative with respect to x, and then we use chain rule whenever we have a y, because we assume y is defined implicitly in terms of x. In other words, y is kind of a function of x. But here, for x squared y, we have two things multiplied, so we use the product rule. Derivative of x squared is 2x, leave y alone, plus x squared. Derivative of y is 1, but it's a y, so we throw a dy dx on there by the chain rule. So there we have derivative of the first times the second plus the first times derivative of the second. Negative x squared y, don't forget the negative. X squared, or negative xy squared, don't forget the negative, but we also have a product rule. A product, so we'll use product rule. Derivative of x is 1 times y squared plus x derivative of y squared is 2y. And then since it's a y, we use the chain rule. Multiply by dy dx. And don't forget the negative. Equals, derivative of 3 is 0. Derivative of log of x with base 5 is 1 over x log of 5. Again, don't forget the negative. Now all we have to do is put the dy dx's on one side, put the things without dy dx on the other side, simplify and solve. So let's do that. Well, I'm going to use the chalkboard, the whiteboard, to my advantage. And get rid of the parentheses like this. Distribute the negative. So now I'll move these things to the other side. I'll move 2xy and negative y squared to the other side, and the other side becomes a positive y squared, negative 2xy, negative 1 over x log 5. And I left the things with a dy dx on this side. Now you can factor out a dy dx and divide by x squared minus 2xy. So dy dx here equals y squared, negative 2xy, negative 1 over x log 5 over x squared, negative 2xy. So differentiate implicitly. You throw a dy dx on every term on which you take the derivative of a y. Then you simplify and solve. Well, I guess you don't have too much simplifying, more move terms around and then solve. The last one, part G, cosine x to the tangent x. Y equals cosine x to the tangent x. Well, here we have x's in the base and the exponent. So we'll throw a logarithm on this and then differentiate implicitly. Throwing a logarithm will turn this side, the right side, into a product. So we have log of cosine to the tangent comes out in front, so you have just tangent log cosine. Well, differentiate implicitly, left side you get 1 over y, dy dx by chain rule, and on the right side we have another product rule. Derivative of tangent is secant squared, leave log cosine alone, plus tangent x times derivative of log cosine. Derivative of log cosine, 1 over cosine, times the derivative of cosine, which is negative sine. And I'm going to put the negative out here. So we have derivative of tangent times the second plus tangent times derivative of the second, derivative of log cosine, 1 over cosine, times negative sine. And then solve for dy dx. Multiply both sides by y. Y is cosine of the tangent. And on this side we get secant squared x times log cosine x. And notice this next term, sine over cosine is just a tangent. So we have a tangent times another tangent, also known as tangent squared. So throw a logarithm on it, and then take the derivative implicitly. And why is my computer not? There it is. Okay. My computer wasn't turning on for a moment. Number 2. What does number 2 say? Number 2 is probably the related rates question. Number 2 is the related rate. You and a helicopter are at the same point. Great. Let's say it's right there. The helicopter begins rising at 25 feet per second. Okay? There's one variable. Let's call it x. 3 seconds later, you begin running at a rate of 11 feet per second. Let's assume you're running in that direction instead of this direction. Doesn't make a difference. But you're running, creating another variable quantity. Call it y. Find the rate at which the distance between you and the helicopter is changing 1 second after you begin running. Well, the helicopter's up here, you're over here. So right there, that line is going to measure the distance between you and the helicopter. We have a right angle, so you get x squared plus y squared equals z squared. So now, let's translate the question into a calculus question. So the question is asking what? Find the rate at which the distance between you and the helicopter is changing. Find dz dt. Because z measures the distance between you, down here, and the helicopter, up here. So this one wants find dz dt. Well, when does it want dz dt? Well, it tells us the helicopter begins rising at 25 feet per second. So dx dt equals 25. I'm not going to give you a problem where the units are like where it says like feet per second and miles per hour. I'm not going to do that. I don't care about unit conversions in this class. dy dt is 11 feet per second. And what are x, y, and z? Well, the helicopter begins rising at 25 feet per second. 3 seconds later, you begin running at a rate of 11. Find the rate at which 1 second after you begin running. So you're running for 1 second, which means the helicopter has been rising for 4 seconds. The helicopter rising for 4 seconds, 25 feet per second. 4 seconds at 25 feet per second is 100 feet. So x equals 100. Y? Well, you're running for 1 second at this point, not 4 seconds. So y equals 11. And we'll also need z. How do we find z? Well, we use this equation or Pythagorean theorem. 100 squared is 10,000. 11 squared is 121. Those added together is 10,121. And you don't have to simplify that. So the square root doesn't simplify. You don't have to simplify the square root. I just stepped on the microphone. You don't have to simplify a square root, even if it's square root of like 32. You don't have to say that's whatever it is, 4 root 2. This square root happens to not simplify. I did check. It's 29 times 4, not 29 times 300 something, 349 I think. But you don't have to simplify the square root. Just 10,000 plus 121. So now all we need to do is differentiate this function with respect to time. X, y, and z are all functions of time. So dx dt, dy dt, and dz dt all show up when we take the derivative with respect to time. Well, now we just have to substitute these 5 numbers and solve for dz dt. Well, first I'm just going to get rid of a 2 from each thing. Divide everything by 2 so we don't have to deal with 2's. Solve for dz dt. Could substitute then solve. I'm going to do them both at the same time. This divided by z, so I'll write that as 1 over z times x dx dt plus y dy dt. That's a parentheses. So 1 over z, 1 over root 10,121 times x dx dt, 100 times 25, 2,500, plus y dy dt, 11 times 11, 121. So we get 2621 over 10,121 under square root, and we have feet per second, I believe the units were. So set it up, label the variable quantities, translate the question, differentiate, substitute, and solve. In many high schools, they really drill into your head this idea that square roots in the denominator, for some reason, are bad. I don't know the reason they do that. I've been told the reason they do that, and I found it quite unsatisfactory. As a matter of fact, I think it negatively impacts trigonometry understanding to always simplify those. So I never require it. Number 3, the volume of a cube decreases at a rate. Find the rate at which, another related rates. Find the rate at which the side length is changing when the volume is 125. So we have a cube. We're concerned with volume and side length. I'm not going to draw the cube. We're concerned with volume and side length. The volume is decreasing at 10 inches per 10 cubic inches per second. So dv dt is negative 10. So let's translate this question. That says that this is an S. Negative 10 because it's decreasing. Find the rate at which side length is changing. Well, I guess I will draw a cube. I'm used to the variable x, so the side length will be x. Find dx dt. when dV dt is negative 10 and the volume is 125. Well, okay. So let's differentiate this function with respect to time. So on the one side you get 1, volume's a function of time, so you get 1 dV dt equals 3x squared dx dt, because x, the side length, is also changing as time is changing. Well, now we just have to substitute and solve. dV dt, negative 10, equals 3x squared. What is x? I don't see any x's on this board. Well, I guess I see one x. I don't see x isolated on this board. I see v isolated. We can use that to find x. The cube root of 125 is 5. So x equals 5. dx dt. Solve for dx dt. Divide by, what is that, 75? So negative 10 75ths. Directions always say simplify fractions. So divide everything by what, 5? Negative 2, 15. Oh, I think I wrote 25 in the solutions. The PDF of the solutions. Whatever. What are our units? Inches. Side length is measured in inches per second. 75 divided by 5 is 15. And notice the answer is negative, and that makes sense, because if the volume is decreasing, then we would expect the side length to also decrease. It is a cube, so all side lengths are decreasing at the same rate. And in that one, volume and side length were functions of time. Evaluate each limit using L'Hopital's rule. Limit as x approaches 3 of what? 3x squared, negative 8x plus a negative 3 over x squared and a negative 9. Well, you try substituting, you get a 0 over 0. You get 27 minus 24 minus 3 over 9 minus 9, so that's 0 over 0. Apply L'Hopital's rule. I will use an h when I use L'Hopital's rule. That limit now equals this limit. Derivative of the top, 6x minus 8. Derivative of the bottom, 2x. Hope you can substitute. In this case, you can, because you get 18 minus 8 over 6, which is what? 12/6, not 12/6, 10/6, which is 5/3. Now that one you could have also solved with factoring, but the directions did say to use L'Hopital's rule. Next one, limit, same function, but instead of letting x go to 3, we let x go to infinity. Now as x goes to infinity, the top goes to infinity, the bottom goes to infinity, so we have an infinity over infinity. We can apply L'Hopital's rule, and it equals the limit as x goes to infinity. Derivative of the top, 6x minus 8. Derivative of the bottom, 2x. As x goes to infinity, this does not approach a number. Well, the way this is written, it does not approach a number. Because the top goes to infinity, the bottom also goes to infinity. So we need to apply L'Hopital's rule again. And it now equals this limit. Derivative of the top is 6, derivative of the bottom is 2. 6 over 2 is 3. Limit as x goes to infinity of 3 is 3. Next, find this limit as x goes to 0. This is C from number 4. Limit as x goes to 0. X plus 1 to the 1 over x. Did I write that right? Yes. I probably should have made that a 0 from the right. Let's assume I made it a 0 from the right. Now let's leave it. Whatever. This takes the form 1 to the infinity. Let's make it to the right. This takes the form 1 to the infinity. So we will throw a logarithm on it. So this equals something. To figure that out, we will compute this limit. Now the reason I threw this plus sign on here is so that the limit of that exponent would be infinity. If it weren't, as x approaches 0 from the right, that limit on the top on the exponent is technically non-existent, and it's not an infinity. That's okay. Don't worry too much about that. Take a logarithm of this function, the 1 over x comes out in front, and we'll just rewrite this as one fraction and hope that it's in a form on which we can apply L'Hopital's rule. As x approaches 0, the top goes to log of 1, which is 0. The bottom goes to 0. So we have a 0 over 0. We can apply L'Hopital's rule, and we get limit as x approaches 0 on the right. Derivative of log of x plus 1 is 1 over x plus 1 times 1, because the derivative of x plus 1 is 1. All over derivative of x, which is 1. As x goes to 0, this goes to 1 over 1 over 1, which is 1. So we have that limit is 1, but that's not the limit we wanted. We wanted this limit. To get rid of the logarithm, take exponentials. So exponential of everything leaves us with e to the first power, which is e. Next, limit as x approaches 0 from the right, part D. Limit as x approaches 0 from the right. What was it? X log x to the 4. Yes. So right here, you try substituting 0, you get a 0 times a negative infinity. Because the log function looks like this, remember. And as x approaches 0 from the right, this goes down lower and lower. And we say that limit is negative infinity. So to deal with the 0 times infinity, we take this 0 and we put it in the denominator, like this. Log of x to the 4 over 1 over x. So that now, this limit is in the form of a negative infinity over an infinity. We can apply L'Hopital's rule on that form, or on a limit that takes that form. So limit as x goes to 0 from the right, the bottom, negative 1 over x squared, the top, four x cubed over x to the 4. Because you get 1 over x to the 4 times 4x cubed. And of course that simplifies. I'll simplify that to just 4 over x. Well, we have a fraction with lots of layers, so let's just turn that into one fraction. Still haven't taken a limit. So we have a negative 4. We have x in a denominator times an x squared in a numerator. X squared in the numerator, x in the denominator gives us just x. And as x goes to 0, that goes to 0. 4x goes to 0. So this limit is 0. This limit may have been a little easier to deal with if you used an exponent rule at the beginning to get rid of that 4, a logarithm rule to get rid of that 4, just turn it into 4x log x. I left it. Problem 5. The position in feet of a particle at t seconds is given by this equation. S of t is t cubed, negative 6t squared, positive 9t. Part A, what is the velocity after 4 seconds? So we need the velocity function, which is the derivative of position. So 3t squared, negative 12t, positive 9. Part A says, what is the velocity at 4? So we need to substitute 4. 3 times 16, negative 12 times 4, plus 9. And that equals 9 because 48 minus 48. Feet per second. I'll just say it's 4. Part B, when is the particle at rest? Well, the particle's at rest when it's stopped, which means the velocity is 0. Velocity, remember, is change in distance over change in time. So the particle will be stopping when the change in distance is 0. So set this equal to 0. I'd like to factor it first. First, you can factor out a 3 because all those things have a 3 on them. Now, I don't like factoring things without 1s in front of them. So let's get rid of that 3. So now we have t squared negative 4t, positive 3, negative 3, and negative 1 make negative 4, negative 3, and negative 1 make positive 3. So this equals 0 when t equals 1, and it equals 0 when t equals, I guess I should say r. I was right the first time. So it equals, that's an r. It equals 0 when t equals 1, and it equals 0 when t equals 3. So it equals 0 at 1 or 3. Part C, find the distance the particle travels on the interval 1 to 3. I intentionally chose where they were both 0, so you had less thinking to do. Find the distance. If I said the interval 2 to 4, you'd have to break it up at 3 and then deal with that. But I just said the total distance traveled on the interval 1 to 3. So let's find the position at 3, and let's find the position at 1, and we just subtract them and take an absolute value, or just, you could just view that as taking the positive number. And I think absolute value is a little complicated to think about here. S at 3. What's S at 3? 27, negative 54, positive 27. That equals 0. It's at position 0 after 3 seconds. Notice the velocity and the position are 0 after 3 seconds. Coincidence. Position at 1 is 1 minus 6 plus 9, which is 4. So between time 1 and time 4, it went from position 4 to position 0. So 4 feet is how much it moved on that interval. Using a linear approximation, find a reasonable approximation for the fourth root of 15.8. Okay? The fourth root of 15.8. Well, the first observation is we know the fourth root of 16 is 2. So let's find the linear approximation near 16. So here our function will be x to the fourth, x to the 1/4. The derivative of that is 1/4, x the fourth minus 1, negative 3/4. And we're concerned with what happens near 16, because that's what we know about. F of 16 is 2. F prime of 16 is what? 1/4 times 16 to the negative 3/4. It's an eighth, because what? The fourth root of 16 is 2. 2 cubed is 8, and the negative throws that 8 in the denominator. So we get 1/32, and now we can find our linear approximation. Is the starting point 2 plus the derivative 1/32 times x minus 16. I feel like the answer I wrote in the solutions is not the same as this. But I might be thinking about the one I put on the test, because I also wrote that yesterday. Well, whatever. This solution's correct. So where were we? Well, we need to just now substitute 15.8. So it's 2 plus 1/32 times 15.8 minus 16 equals 2 plus 2 minus 1/32 times 1/5. So that this decimal is negative 0.2, which is negative 1/5. I just threw the negative out there. So it equals 2 minus 32 times 5, 160. Why is 32 times 5 160? Well, you could count 32, 64, 96, 120, 160. Or you could do 32 divided by 2 is 16, and then throw a 0 on it. Because multiplying by 5 is the same as multiplying by 10 and dividing by 2. And you don't have to simplify that to a final number. You could leave it as 2 minus 1/160th. I don't remember that being my answer. I'm going to have to check my solutions. And this one's correct. So maybe I just did it too quickly when I wrote the solutions on paper. And the last one is a differentials question. What does it say? The radius of a sphere is measured to be 4 inches with a possible error in measurement of 0.5 inches, 0.05 inches. So we have a sphere. The volume is given by 4/3 pi r cubed. What is the maximum error in using, what is an estimation, it should say, for the maximum error in using this value of the radius to compute the volume? Well, we just use a differential to find that estimate. Derivative here, 4/3 and pi are constants. Derivative of r cubed is 3r squared. So the 3 and the 3 cancel, and you're left with 4 pi r squared dr. So 4 pi, the radius was measured to be 4. It's a lot of 4s. And the dr is 0.05. A nickel is a 20th of a dollar, so that's 1/20th. And then you get what? 64 pi over 20. And then you have to reduce that. 32 pi over 10, you have to reduce that. Something over 5. 16 pi over 5. And the radius is the volume is measured in cubic inches. So having this error in the radius will result in approximately this much error in a computed volume. So let me know if you have any questions on these. The exam was written by copying and pasting this onto my exam formatted page and just changing the questions around. So it will look quite similar. I'm pretty sure it's also 7 questions with parts, of course. Lots of derivatives, so definitely be sure you know how to do number 1.